students, today's topic of biomolecules will be the structure of DNA. Before starting, I want to ask you two questions. Will you please tell me what are the different types of sugars present in RNA or DNA? Any one of you?
In RNA there are ribose sugar and in DNA there are deoxyribose sugars.
So in RNA, as the name indicates, it is ribonucleic acid. The sugar present is ribose, and in DNA, as the name indicates, this is deoxyribonucleic acid. So the sugar present is deoxyribose. Okay? Any one of you can tell me what do you understand by the double helical structure of DNA? Yes, Ashu?
There are two strands which are coiled with each other and in an anti-parallel fashion.
That is the coiled running antiparallel to each other. So that is a helical formation. So this is the double helical structure of DNA. Sit down. So who proposed the model of DNA? Rashi?
Watson and Crick proposed the DNA in 1953 and they got Nobel Prize for it.
That is, they got Nobel Prize for proposing the structure of DNA in 1962. Sit down. So now coming to the structure of DNA. DNA is the largest molecule. That is the macromolecule. It consists of three parts. That is sugar. As you already told, the sugar is deoxyribose sugar, then phosphate group, and the nitrogen bases. Phosphate deoxyribose sugar is a 5-carbon sugar, then H3PO4 is the phosphate, and nitrogenous bases, they are of two types, that is purines and pyrimidines. Purines are 9-membered ring and pyrimidines are 6-membered ring. So what are purines? Adenine and guanine, they are the purines. Thymine and cytosine, they are the pyrimidines. Now moving further, DNA is a ladder-like structure. Ladder as we use in homes, this is like this. DNA structure is also like this. How is it arranged? This is the backbone. This is the backbone, and in this the steps they are joined. You can see here also. See, these are forming the backbones like this, and these are the steps joined. Okay? These are forming the backbones, these are the steps joined over here. So the ladder-like fashion of DNA, that is like this. The sugars and phosphates, they form the backbone of the DNA. Sugar, then phosphate, then sugar, then phosphate, then sugar, and then phosphate, and so on. Opposite to sugar is the sugar, opposite to phosphate is the phosphate. Again, opposite to sugar is the sugar, opposite to phosphate is the phosphate. Sugar phosphate molecules, they alternate with each other. The nitrogenous bases, that is purines and pyrimidines, they are attached with the sugar molecules. Adenine and thymine always pairs with each other with 2 hydrogen bonds. Guanine and cytosine always pair with each other with 3 hydrogen bonds. You can say one purine always pairs with one pyrimidine. Okay? So sugar, this is, supposing we can say here it is A, supposing here it is T, supposing here it is G. Again the nitrogenous bases, they will join with the sugar molecules only. A always pair with T, so here will be T with 2 hydrogen bonds with A. Here will be A with 2 hydrogen bonds with T. Here it will be C with 3 hydrogen bonds with G. Okay? Now moving further, this is the simple how DNA molecule that is arranged. One sugar, one nitrogenous base, and one phosphate molecule. This forms the nucleotide. see, we say there are neurons present in the nervous system. That is a unit of nervous system. Nephron is a unit of kidney. We say like this. So nucleotide is a unit of DNA. Many nucleotides are joined together with each other. Many units are joined together with each other. They form the structure of DNA. Yeah. Now this is just a simple way to tell you how these are arranged. But they are arranged by coiled fashion. That is, they are running anti-parallel to each other. Now what do you mean by anti-parallel to each other? See, there is a sugar molecule that is deoxyribose sugar. Its structure is like this. This is first carbon, this is second carbon, this is third carbon, this is fourth carbon, and this one is fifth carbon. Okay, we will start from here. Here it is oxygen present. One carbon, two carbon, third, fourth, and this one is fourth. This one is third, this one is second, first, and this one is fifth carbon. Whatsoever is the direction of sugar molecule present, we consider the direction of DNA strand. And DNA always run in 5' to 3' end. The direction of DNA is always from 5 to 3. Here it is 5, so here it is 3. So we will be moving further to the biomolecular structure. Okay? How is it arranged? I will be drawing sugar molecules that is like this. One sugar, this is second sugar, this one is third sugar, this is 1, 2, 3, 4, 5, right? This is again 1, 2, 3, 4, 5, again 1, 2, 3, 4, 5, right? Now see, supposing this is 5, this is 3. What will be the direction of another strand? It will be like this. This will be 3, this will be 5. Okay? So if one sugar is drawn like this, the other will be like this. I will draw it like this. This is 1, 2, 3, 4, and fifth will be on this side. So that's why 3' to 5'. So they are running parallel, anti-parallel. So anti-parallel. This is the reason. Okay? So second one, it will be like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. Okay? So this is the position how the sugar molecules they are arranged, and they are running anti-parallel to each other. 5' end, here it is, last one is 3' end. Here it is 3' end, last is 5' end. So the direction will be 5 to 3, 5 to 3. Here it is 5, here it is 3. This is the direction of DNA strand. Here it is 5, here it is 3. This is the direction of DNA strand. 5 to 3, 5 to 3. Running anti-parallel to each other. Now what about the position and the bonds in the DNA molecule? The phosphorus, here it is phosphorus. It is attached to the third carbon of the sugar which is placed above it, and fifth carbon of the sugar which is placed below it. One bond with this sugar, one bond with this sugar. This is an ester bond, this is an ester bond. So the bond is phosphodiester. Two esters with phosphorus, so this is a phosphodiester bond. Again there is phosphorus with the third carbon with the fifth carbon. This is again in continuation, this means this is joined with the phosphorus bond. This is again in continuation, this means this is joined with the phosphorus. Here also you can see fifth carbon here, third carbon here. Fifth carbon here, third carbon here. Again diester bond, phosphodiester bond. Again this is in continuation and this is in continuation. Is it clear? So this is a phosphodiester bond, and the bond between two nitrogenous bases, that is purines and pyrimidines, is hydrogen bond. Two hydrogen bonds between A and T, three hydrogen bonds between G and C. Now how they are arranged? They are arranged with the first carbon of both the sugars. First carbon of the sugars, they are lying inside. So supposing here it was A, here it is T, T here is attached with the first carbon sugar and nitrogenous base, phosphodiester bond between phosphorus and sugar, and hydrogen bonds between two nitrogenous bases. For example, here is G, here it will be C. C will be joined to the first carbon, G will be joined to the first carbon with 3 hydrogen bonds. Supposing here it is T, here it is A. They will be joined with 2 hydrogen bonds, but glycosidic bond between the first carbon of the sugars. So this is how they are arranged. Is it clear? Any problem still here? Anyone having any problem? Clear to everyone? Okay. Now moving further to draw the diagram of DNA. See, this is a double helical structure. It moves like this. This is one strand. This is another strand. Moving, running anti-parallel. What are these shown between them? These are the nitrogenous bases. We will be drawing this as such on the plan. A very easy method to draw. But what students do, they directly draw like this. This is wrong. This is not the shape of DNA. This is totally a wrong method to draw. Very simple method is, see there are 2 strands running anti-parallel to each other. This means you have to draw 2 strands which are like parallel but direction is opposite. Okay? I'll tell you the simple way. See, supposing I divide the sheet into 3 parts, equal parts. You can draw a dotted line, very faint. This much is the direction, this much will be the distance. Okay? Start from one side, give a turn, again give a turn, right? Now draw a line coming parallel to this. Again give a turn. So this is the structure of it. Supposing this is 5' and this is the line going on. This one, so this will be 3'. So this will be opposite 3' and it will be 5'. This you know, right? Now you have to draw sugar and phosphate bases in this. See, from here till here. This is one coil of DNA, one turn of DNA. One turn of DNA is, now you tell me, how much is the length of one turn of DNA? This is 3.4 nanometers, right? 3.4 nanometers, or we can say 34 angstrom units. Nanometers means 10⁻⁹, angstrom unit is 10⁻⁻². So that is nanometers means 10⁻⁻9 meters. So this is one turn of DNA. If we are taking turn of DNA from this side, so it will be from here till it turns to the other direction. That will be one turn. In one turn of DNA, can you see a groove over here? Can you see a groove over here? There is one major groove and this is one minor. One major groove and one minor. Now on this is the backbone. Backbone where we have sugar and phosphate molecules. So you just draw sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate, alternating with each other. Like this. Again on the opposite side you can draw sugar, then phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate, and so on. alternating with each other. In one turn, there are 10 bases. So I have drawn 1, 2, 3, 4, 5, 6, 5, 6, 7, 8, 9, 10 bases. 10 sugar molecules. Because 10 bases are arranged in one turn of the year. So supposing here it is A, it will be double bond T with this sugar. Supposing this is T, it will be double bond A opposite to the other sugar on the other strand running anti-parallel to each other. Supposing this is G, triple bond C with the sugar. Supposing this is C, triple bond G with the sugar. Again A, double bond T with the sugar. T, double bond A. G, triple bond C. C, triple bond G. A, double bond T. T, double bond A. Right? So as its length is 3.4 nanometers, there are 10 base pairs involved in this. The distance between each base pair is 0.34 nanometers. 3.4 divided by 10. Simple. 3.4 is the distance of one point, of one turn. 10 base pairs there are arranged in this. We just divide by 10, then equally placed, so it will be 0.34 nanometers. That is 3.4 divided by 10, it will be 3.4. Divided by 10 will be what? 0.34 nanometers or 3.4 angstrom units. Because that is 10 raised to minus 10. So it will be this much. Okay? This is a form of DNA which we say it as bDNA. DNA is of different types. This is bDNA. There are other forms of DNA also: aDNA, bDNA, cDNA, tDNA and zDNA. In bDNA there are 10 base pairs. In between one pair, in between one coil, in one we can say the turn of DNA. In A there are 11 base pairs. In C there are 9 base pairs. In D there are 8 base pairs. In Z the basic thing is that is it is zigzag in nature. The backbone of Z DNA is zigzag in nature. Here we have a straight backbone which is coiled, which is running anti-parallel to each other. But in Z that is it is zigzag. Okay. Now moving further, the distance between we can say the diameter of DNA. What is the diameter of DNA? This much. That is 20 angstrom units. 20 angstrom units. And this much is the diameter which can accommodate one purine and one pyrimidine. Now the question arises, why not two purines join with each other? Why not two pyrimidines join with each other? The very simple answer is, purines they are 9-membered ring, pyrimidines they are 6-membered ring. Supposing in this, both the rings they are of 9 members. Both the rings they are 9-membered rings. This means two purines are present. So the distance is such that it cannot accommodate two purines which are larger molecules. They will be very close to each other. And why not two pyrimidines? They are 6-membered ring. They are small molecules. The distance is such, if two pyrimidines are placed in this, the bonds will be very weak between them. The hydrogen bonds will be very weak in them. So that's why the distance is such that it can accommodate one purine and one pyrimidine. These are all according to Char capsules. That is A always pair with T, A always pair with T with 2 hydrogen bonds, G always pair with C, G always pair with C with 3 hydrogen bonds. The number of A, that is adenine, is equal to the number of T molecules, that is thymine. The number of G, that is guanine, is always equal to the number of cytosine molecules, that is. Okay. So now moving further, this is the structure of DNA, 5 to 3, 3 to 5, running anti-parallel to each other. This is the same thing. See, it is coming, running 5 prime to 3 prime, 5 prime to 3 prime, and what has been shown over here is semi-conservative nature of DNA. Semi-conservative nature of DNA means whenever replication of DNA takes place. Replication means 2 copies are formed. From one DNA molecule, 2 molecules are formed. They are packed with each other with a histone protein molecule, octamer. 8 histone protein molecules are there, that is known as a nucleosome. Whenever this is there, when they get separating, that is when unwinding of DNA molecule take place. One will be the parent strand, one will be the new strand. Here also one will be the parent strand, one will be the new strand. So whatsoever the new strands, the two new strands they are formed, replication is there, they are having 50% parental DNA, 50% new DNA. Again 50% parental DNA, 50% new DNA, that is known as semi-conservative nature of DNA1. So this is the structure of DNA molecule. Now few properties are there, that is, for example, renaturation and denaturation. What is this? Renaturation and denaturation. See, on heating at high temperature, supposing we are boiling egg at home, that has protein molecules. What is the fate of the egg? Either it gets crumpled, egg glutination takes place, but it cannot come back to its original shape, original position. Whatsoever has been changed is changed. This is the difference in DNA. Whenever heated at high temperature, it breaks down its bonds. It is not in its own position. It is not in its shape. That is known as denaturation. Denaturation. D. Again on cooling, it again regains back its original position. That is known as renaturation. R. Denaturation. On heating it is off. And again on cooling, it is again coming back to its original position. That is known as denaturation. Next is polarity. Polarity means it is bipolar. 5 to 3, 3 to 5. So these are indicating the polarity of DNA. That is, sugar molecules are there. One is 3' and one is 5'. So this is bipolar. Next one is variety. These are the types of DNA. The students get confused with that this is the variety of DNA. This is not a variety of DNA. These are the types of DNA. Variety means, see, 99.9% of human genome is same. Genome means the DNA is same. What we have? We have sugar, we have phosphate, we have nitrogenous bases. It is only the arrangement of nitrogenous bases by which we all are different from each other. Is anyone having any similarity to each other? No. Only the parents, their children, they are similar to their parents. That is, parents and the children, they are having the similarities in the genome, in the genetic makeup. Otherwise, this is the arrangement of nitrogenous bases which is making DNA different for each and every individual. Whether it is humans, whether it is plants, whether animals, everything that is making different for each other. So this is the variety of DNA. Is it clear? Anything you want to ask, please. Anything you want to ask? Is it clear to everyone? Is it easy to make by making 3 lines so that it is convenient to make in a proper shape and in a proper dimensions? That is very much important. So that's all for the structure of DNA. This is the genetic material carried over as such to the next generation. DNA helps in replication. After replication, it helps in transcription. After transcription, it helps in translation. That is, the flow of information is there from DNA to RNA to proteins. This flow of information is known as central dogma. See, many scientists, they proposed the structure, but it was Watson and Crick who ultimately gave this model of DNA, that is double helical model of DNA, and they were able to fully compile this model in 1953. For this model, they were awarded Nobel Prize in 1962. We can, nowadays DNA fingerprinting is done. What is this for? This is done for 2 things. One is for paternity test, another one is for criminal cases. DNA is similar, almost similar in all the individuals, but DNA can be held from any cell. Whatsoever the nitrogenous bases are present, whatsoever the differences are there in the nitrogenous bases, that make DNA unique in every individual. By which those tests can be done, that is the paternity test and in the forensic lab sciences, the criminal test. Is it clear? That's all for DNA structure. Clear to everyone? Thank you so much.